Adjustment with my microphone that feeds audio to our website recording. I forgot to turn off the microphone last time, so the batteries died. So I put in new batteries, and away we go. Special quiz 1 is posted. How many of you have looked at it? Okay. Have fun. That's what it's all about. All right. As usual, the various discussion classes made different degrees of progress. So, to try to be sure that everybody gets the same treatment, for some of you, what we shall do initially will be review, but that won't hurt. Because this stuff is stuff you've not seen before, it's challenging stuff, and it's important stuff. Back to our 10th molar aluminum sulfate solution. Last time here, we wrote the principal species charge balance equation for that system and set it equal to the charge sum of 0.60. Discussion class yesterday, we wrote the all species charge balance equation for this system, which in addition to hydrated aluminum ion and sulfate ion contains hydronium ion, hydroxide ion, and hydrogen sulfate ion. And recognize that still is equal to the charge sum of 0.60. Why? Because on the anion side of the fence, at least this is the simplest way to realize why the charge sum is still 0.60. This is an acidic solution. So the hydroxide ion molarity, whatever it is awful small next to 0.60 because it's at the minimum less than 1 times 10 to minus 7. And the hydrogen sulfate ion is also quite small because, as you did yesterday in discussion class, the reaction of hydrated aluminum ion with sulfate ion to make hydrogen sulfate ion and the conjugate base of hydrated aluminum ion, which we refer to with Al 2 plus quotes, okay, is a small extent reaction. So, whatever the hydrogen sulfate ion molarity is in this solution, it will not be a value which is large enough to add to 0.60 and make 0.60 increase. Now, 1 or 2 members of the discussion staff told me that some people were asking, why do we keep hydronium ion in that equation? Well, if you want to calculate the hydronium ion concentration for the solution, obviously you have to keep it in there. Otherwise, you don't have to keep it in there. Really. If you want to get a gee-whiz concentration for hydrated aluminum ion itself or sulfate ion, you don't need the hydronium ion. You got to pay attention to what the question that you're faced with asks you to do. That's where it all starts. What am I being asked to do? Okay? And then, yesterday, you were reminded that for this solution, the 0.10 molar aluminum sulfate solution, you can likely calculate correctly the hydronium ion molarity from Ka1 only. Now, to recognize this, let's make a comparison of this solution to 0.010 ferric nitrate solution, which we already have looked at least to a certain extent. What's the difference? Difference number 1. Ka for hydrated iron plus 3 is 4.0 times 10 to minus 3, whereas Ka for hydrated aluminum plus 3 is 1.4 times 10 to minus 5. Big difference in K values. And on what does percent or extent of ionization depend? Ka, So we know the ionization extent in the aluminum sulfate solution of hydrate aluminum ion resulting in the production of hydronium ion is not nearly as great as it is for hydrated iron plus 3. Same conclusion follows from comparison of the initial molarities. Because the more dilute the solution, the greater is the percent ionization, or ionization extent. The iron nitrate solution is 100th molar. This solution is 10 times more concentrated. So that's going to limit the ionization extent. So we looked at two reasons why we know for sure the ability of hydrated aluminum ion in the aluminum sulfate solution to react with water and make hydronium ion is nowhere near the ability of hydrated iron plus 3 to do the same thing on reaction with water to make hydronium ion in the 100th molar iron nitrate solution. So I've written this on the board. And then, as a number of you recognized yesterday, let's calculate the hydronium ion concentration, not from this equilibrium, but from Ka1 only, which means we'll take Ka1 and apply to it x squared over m sub I minus x. So you got x squared over 0.10 minus x is equal to 1.4 times 10 to the minus 5. Get the hydronium ion concentration from that calculation and that calculation alone. And then we get to the bottom line. What's the bottom line? What's the only real dictator, if there is such, in science class? It isn't the person who stands in front of you and may on occasion act like a dictator. It isn't anything written in any textbook. It isn't any calculation or idea that the smartest person in the world has ever had or done. It's the experimentally verifiable result, because that's what nature is. So if we want to know if this calculation that we've done to get the hydronium ion concentration for the aluminum sulfate solution is correct, we go to the laboratory and in a meticulous fashion prepare the 0.10 molar aluminum sulfate solution. Meticulous meaning painstakingly careful. And with a good pH meter, measure the hydronium ion concentration. And if the measured hydronium ion concentration is the same we got from the calculation, bingo, we did it right. And if we find the hydronium ion concentration is, by measurement, greater, then we know the second ionization is also making a contribution. Now, I haven't done this experiment, but I will bet that if I pursued the calculation involving the second ionization, I would find out that the contribution to hydronium ion molarity in the aluminum sulfate solution is negligible. And I will bet then that the calculation to get hydronium ion after applying x squared over m sub I minus x to the first ionization to Ka1 only will give me the hydronium ion concentration the same as I will find by experiment. That's my bet. And this, for you folks at this stage of the game, as I see it, is the most difficult part of chemistry. Because so far, in chemistry class, you've been led to believe that we can calculate the answer to any question given. Ha ha ha! Nothing could be further from the truth. That's why I tell my people who do 2045, you've got to expose these people to chemistry. They come in the 2046 class thinking all you have to do is to push damn buttons on calculators and you can answer any problem there is that exists in the world of chemistry. Nothing could be further from the truth. This is an illustration of why. We're looking at a case where we do not, on a for sure basis, know the answer. We have to do the experiment to find out. How many times in 2045 did the people who lectured the information to you talk about doing an experiment to verify what they brought to you in class? I'll bet never. Which is another reason why they didn't do chemistry. And that's not fair. But I'll do the best I can to get you past that shortcoming. And I'll also do the best I can to get them up to speed. Sometimes they look at me like I'm crazy. You're damn right I'm crazy. I'm crazy about this stuff. I want it to be taught so that it in fact meshes with nature and the way nature operates. That's the only way you can really do science. All right, on we go. Enough of that sermon. Another one will come up soon, you know that. Back to the iron nitrate solution. What should we do to pursue calculation of the hydronium ion molarity for the iron nitrate solution? Well, ultimately, after we add the charge balance equation and material balance equation to this stuff, I like to have an idea of what the hydronium ion molarity is before I start doing all the rigorous analysis that follows from the combination of the equations that I write from Ka1, Ka2, charge balance, and material balance. So here's how we get a handle on that. Let's take the first ionization for the iron nitrate solution, at least for the immediate moment, as the only source of consequence of hydronium ion. That's what we did for the aluminum sulfate solution. What will this give us? It will give us the minimum possible value for the hydronium ion concentration. Because if the second ionization makes a contribution, which we know for sure it does for the iron nitrate solution, we know the true hydronium ion concentration will be larger than this minimum possible value. So we go through this rigmarole of applying x squared over m sub I minus x to Ka1. Here's Ka1. Here's the Ka1 value. There's the chemical formula of the equilibrium constant. And then I put quotes on this equal sign. Why did I put quotes on this equal sign? Is this really an equality? No. It's approximation. It's approximation which we use to get this minimum value of hydronium ion concentration. There's m sub I. We do the indicated arithmetic. We recognize this is an expression which, in order to solve, you cannot forget x in the denominator. So it is a quadratic which has to be solved. But you know, I'm not doing any quadratic formulas to get this stuff, because it interferes with my knowledge and understanding of chemistry, and I'm not having that. So I speculate on percent ionization. I find out that after trying the value that I should try first, which is 50%, okay? Because what does 50% give me? It gives me half of m sub I. 5.0 times 10 to minus 3. Okay? 5.0 times 10 to minus 3 is pretty close to, but a little bit larger than this. Hey! So I know the true percent ionization, a little bit smaller, 50%. I find out that it's 46% when I do more scratch arithmetic, and I get the minimum value for the hydronium ion molarity for this solution as 4.6 times 10 to minus 3. And now I ask the question, for this solution, what is the maximum possible value for the hydronium ion molarity? I've told you what it is there. You all see where that number comes from? 2.0 times 10 to minus 2?
If the second ionization reaction goes to 100%.
Yeah, if the first ionization goes 100%, remember this is 100th molar iron nitrate solution. If the first ionization reaction goes 100%, I've established a minimum molarity of hydronium ion of 100th molar. And if the second ionization goes 100%, there's no other sources of hydronium ion in here. Water plus water won't mean anything in a solution this acidic. So if the second ionization also goes 100%, that adds another 0.010 moles per liter to the hydronium ion molarity. That gives me twice the m sub I value. I'm just letting the equations for the reactions, Ka1 and Ka2, talk to me. That's all I'm doing. So, without anything fancy, because we've not done yet anything fancy or difficult, we've not yet done anything with MB or CB, we know the hydronium ion molarity for this solution is inside this box. I could rewrite this as 20 times 10 to the minus 3. You realize there's not many data points in between 4.6 times 10 to the minus 3 and 20 times 10 to the minus 3. There's 4.7 times 10 to the minus 3, 4.8, 4.9, 5.0, 5.1, and blah, 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 till you get up to 20. One of those numbers is the answer. And I'll pursue, in a rigorous fashion, calculation of hydronium ion molarity along with Ka1 and Ka2, considering MB and CB. And I expect you're probably saying, at least if you're wanting to learn this stuff, well, how do I do that? We're going to show you how to do that. Maybe not necessarily for this system, shortly. So hang on. That's the final stuff we do in this chapter on acid-base chemistry. Because after we get to that, you will then be in position to do what I said you'd be able to do when we started this acid-base stuff. In any water solution from now on, after we get this stuff, after one lecture more, something like that, you can take any water solution, and after recognizing the PSI, because you can get that from the label on the bottle, you now know how to pay attention to the reactions that are shown by species that are put in the solution, if they behave like acids or bases. For any water solution, you will now be able to calculate the molarity reliably for any species in the solution whose existence depends on pH. And most species in water solution, in fact, have an existence which depends on pH. Pretty powerful tool. You think biochemists might want to know how to do this? You're damn right. All right. So before we go on with this extended arithmetic, where the MB and CB comes into play, let's ask this question. When is it not possible to equate CB to charge sum? Because if you've understood what a charge balance equation tells you, you've understood that when you can take the sum of the positive ion concentration terms, if you want to calculate hydronium ion molarity, or the sum of the negative ion concentration terms, if, for example, you want to calculate hydroxide ion molarity straight away, okay, and set that equal to a charge sum, then you can throw away the other part of this equation. The sum of the positive ion molarities equals the charge sum, or the sum of the negative ion molarities equals the charge sum. That simplifies the arithmetic you're going to have to do if and when you can take a charge balance equation and equate it to a charge sum. So what's at issue here is, when is it possible to equate a charge balance equation to a charge sum directly from the label on the bottle, M sub I? Okay? Answer. If Prince for principal reaction in the system converts ions to molecules, or converts molecules to ions, then can't equate CB to charge sum. Directly. From M sub I. Now let's back up a moment. We've already recognized that for a solution like iron nitrate, you can set your charge balance equation directly to a charge sum. Why is that true? For the iron nitrate solution, for this solution. Why can you equate the charge sum equate the charge balance equation for this solution immediately and directly to 0.030? Why? Do you see that in this solution the principal negative ion is nitrate ion? And the nitrate ion molarity is 0.030. Because in this solution, nitrate ion exhibits no behavior whatsoever as a Bronsted-Lowry base, even though it's a minus species. Its molarity remains fixed at 0.030. Call it a spectator ion, if you will. But it's in the solution and establishes total moles minus in the system. So there's your charge sum. Same follows for the aluminum sulfate solution. Again, because of the anion. The sulfate ion molarity in the aluminum sulfate solution is 0.30. And when you write the charge balance equation, you've got a 2 multiplier on sulfate ion, don't you? So it gives you a charge sum of 0.60. And sulfate ion is such a weak base that its concentration, even though it does react as a base in this system, the reaction extent involving sulfate ion is so small because sulfate ion is such a feeble, weak base. On what basis do I say sulfate ion is such a feeble, weak base? You looked at this yesterday. Why can I say flatly that sulfate ion is a feeble, weak base? What property of sulfate ion do we wish to know in order to make that statement? KB. 8.3 times 10 to the minus 13. That's pretty damn weak. So, there follows the charge sum. Now let's look at a case where you cannot equate the charge balance equation directly to a charge sum. Ammonium cyanide solution. I mean, there's many examples. I just happen to pick this one because this is the one that's in the notes. So you've got reference information available to support your understanding of this consideration. CB. Simple CB, because in this system there are only 2 positive ions. And they're each bearing a charge magnitude of 1. That's ammonium ion and hydronium ion. And in this system, there are only 2 negative ions. Cyanide ion and hydroxide ion. So there's the charge balance equation. And why do I write the formula for cyanide ion as Nc minus? Because the minus charge in this ion, or for this ion, is on which atom? Carbon. You're damn right. I want these formulas written so they keep with chemical fact. I had fun with a chemistry textbook representative yesterday. It's funny how these textbook general chemistry textbook, when they come here to want us to get us to buy the book, they never send a chemist. They always send the salespeople who know nothing about chemistry. And then they want to talk to me about why I don't want their book. I might as well talk to the wall. They don't know what the hell I'm saying. First thing I asked this guy is, what's the correct formula for hydroxide ion? He didn't know what the hell hydroxide ion is. And he's selling a chemistry textbook. I don't want to bother with people like that. You've already created an impenetrable wall of ignorance. How can we communicate? All right? Why is it not possible to write the charge sum for this charge balance equation from this information? Well, you know how to deal with solutions of acids and bases. You consider the PSI and recognize in the solution that's in question what are the principal acid-base equilibria which exist. And what is that determined by? You've got your PSI before you. PSI for this system, what is it? Ammonium ion, cyanide ion, and water. Now, watch out for this question. Are you sure that's the correct PSI for this system? Is that the correct PSI for this system? No, it isn't. Not for this system. It's a little bit more challenging than what we've looked at before. Why is what I just said not the correct PSI for this system, for this ammonium cyanide solution? Well, we got to go back to the PSI that follows from the label on the bottle. Ammonium ion is in this system, at least initially, the strongest acid present, and cyanide ion is, at least initially, the strongest base present. So, if any acid-base reaction at all occurs in this system, it's got to involve these two things. Best acid, best base. That were used to create the system. And if H plus exchanges between this acid and this base, I make this acid and this base as products. And one of the steps or considerations we've always made when we write equations for acid-base reactions is to, after we write the equation for the reaction, say what about the reaction? Its extent. Well, what are you going to tell me about the extent of this reaction? Well, from a general gee whiz standpoint, the extent of this reaction is large or small? Small. On what basis do you say that? Well, you look at the acid-base table, and you see in the acid-base table, this is found to be a stronger acid than this. And you also see this is found to be a stronger base than this. So extent is small. But I'm going to put quotes on this. And then ask the question, how small? Damn small? Or damn near large? This is where the fun starts. This kind of stuff you got to pay attention to in chemistry, because these ions and these molecules don't give a damn what we think or don't think. So I got to do the best I can to program you to learn how to think about these things, because they're not going to change their behavior and behave in a simpler fashion because some dummy in some general chemistry class who knows not what the hell he or she is doing wishes not to pay attention to the chemical facts. It don't work like that. So take a look at Ka for HCN. The acid-base table, you see it to be 6.2 times 10 to the minus 10. And Ka for ammonium ion is 5.6 times 10 to the minus 10. Woo! These are pretty close strength-wise, aren't they? And you'll find the same on comparing the base strengths. Kb ammonia is 1.8 times 10 to the minus 5. Kb cyanide is 1.6 times 10 to the minus 5. So I believe that it's far more to the point to say for this reaction from an extent standpoint that the extent is about 50%. A little bit less than 50%. Now I could at this stage of the game show you how to get the percent. But for now it's good enough to realize that because of the closeness and strength of the product acid to the reacting acid, or the product base to the reacting base, that the extent is substantial. It approaches 50%. So you now know if you want to write the correct PSI for this system, beside ammonium ion and cyanide ion in water, what also do you have to have in this PSI? What else? HCN and ammonia. How about that? They're all in there as principal species. And it follows from this assessment that we just made. So what are we looking at? We're looking at a system where ions as initial principal species have reacted with each other substantially to become uncharged particles, molecules. So if you were to write this charge balance equation correct and set it equal to 0.10, you'd be way off base. The true charge sum for this charge balance equation compares how to 0.10? Bigger or smaller? Bigger or smaller? Smaller, because this thing turned charged particles into neutral particles, didn't it? And if you look at a reaction where molecules converted to ions, then the charge sum, which you might infer from the label in the bottle, would be smaller than the true charge sum. Because now neutral particles became ions. So, at this stage of the game, all we want you to do is to recognize how and when you can write, after writing a charge balance equation, set it equal to a charge sum. In most cases you can. Because in most cases you'll have a solution where only one of the species is a principal reactant. Point, the iron nitrate solution. Nitrate ion is a principal species, but it doesn't do any chemistry in there. The only thing that reacts substantially in there is hydrated iron plus 3. Back to the aluminum sulfate solution. What's the only principal species in that solution that reacts substantially? Is it hydrated aluminum ion or is it sulfate ion? We answered this question a moment ago. Aluminum ion. Well, for cases like that, writing charge sum is directly doable from the label on the bottle. But here, no. Now then, let's ask one more question. For this solution, a question you were asked to consider, at least in brief, yesterday. A question which we're going to look at in detail probably during our next gathering. What would you do for this solution if I required you to calculate the hydronium ion concentration? This is fun. You're going to need charge balance, you're going to need material balance. And you're going to have to recognize that you can, of course, write the equilibrium constant for this reaction equation. Did you do that yesterday in discussion class for those who did? Okay. It's easy to calculate the hydronium ion constant. The equilibrium constant for this reaction. Because you wind up with the molarity of HCN times the molarity of ammonia divided by the molarity of ammonium ion and molarity of cyanide ion in the denominator. And if you take that expression and multiply it by, guess what? Hydronium ion molarity, hydronium ion molarity. Remember? Multiplying by 1, just like we used when we developed the Kw equals Ka times Kb relationship. You'll find out that K for this solution is equal to Ka ammonium ion divided by Ka for HCN. Now, given that we've recognized Product acid, reacting acid, very similar in strength, just like the product base and reacting base. What do you think this K value is going to be close to without even doing any calculation? 1, you betcha. Because that damn thing is going about 50%. K value of 1 is telling you this thing goes 50%. Okay? But in calculating the hydronium ion concentration for this solution, you have to pay attention to one more detail, one more important detail. And that is, you have to recognize that this thing, with a KB value of 1.6 times 10 to minus 5, compared to this thing with a Ka value of 5.6 times 10 to minus 10. Which of these do you think will be the species initially put into the solution which really controls the solution pH? Cyanide ion or ammonium ion? Cyanide ion. Because its strength value is a whole lot greater than the strength value for the other species. So you're going to start out by knowing the solution is distinctly basic. And you're going to have to recognize, and because of the much greater strength value for cyanide ion, it will react with water to a much larger extent than ammonium ion reacts with water. Which means, here comes the tricky question. You write the K for this, and you have HCN molarity times ammonia molarity. And again, in the denominator, you got ammonium ion molarity and cyanide ion molarity. If you believe in this solution that the only reaction which involves ammonium ion and cyanide ion is this reaction, then the molarities of these two species will be equal. Are the molarities of these two species equal in this system? No. There's the problem. Because the cyanide ion reacts far more extensively with water than does the ammonium ion. And that's the final detail you have to consider to do the hydronium ion calculation. More on that shortly. Okay? Now then, a couple more considerations regarding charge sum. Questions 1859 and 1860. So let's take a look at these questions for today's wrap-up. And I will ask the question after we have this conversation. If you remember the question on exam 1 which related to 1860. Here's the question. Can I, for this sulfuric acid solution, set the charge balance equation equal to a charge sum directly? There's a charge balance equation. That's charge balance equation for each and every sulfuric acid solution if sulfuric acid is the exclusive solute. And the answer for this solution is, I can't set this equal to a charge sum directly from this. Why not? Well, let me ask this question in a different fashion. Will a charge sum for this charge balance equation, if it's not this value, will it be bigger or smaller than this value? Bigger or smaller? Bigger is correct. Why? Why? Because what? Come on, now you're getting the part that counts, the because part. Why is the charge sum for that 10th molar sulfuric acid solution guaranteed to be larger than 0.10? Because?
It's a molecule and then it turns into ions.
Because what happens?
Second ionization goes to a decent extent.
Yes, because hydrogen sulfate ion is going to react and contribute to the hydronium ion molarity. So the charge sum, which is equal to the hydronium ion molarity, is a bigger number than 0.10. Now let's look at the second solution. Quickly, tell me the charge sum for the second solution. What does ionization extent depend on? Ka. Ka for HSO4 minus is 1.2 times 10 to minus 2. That's a hell of a lot bigger than 10 to minus 7. So we know under conditions of extreme dilution, hydrogen sulfate ion can ionize to what extent? 100%. Is this condition of rather extreme dilution? 1 times 10 to minus 5 molar? So tell me the charge sum for 1860. What is it? What is it? It's 2 times 10 to minus 5. Because hydrogen sulfate ion in that second solution is going 100%. Do the arithmetic to prove it to yourself. And we'll pick it up from this point next time.